Hey everyone! Wish you a late Merry Christmas and welcome back to another video. In the last one, we talked about how to add, subtract, and divide complex numbers, which are a whole new system of numbers. In this one, it gets even more interesting. We can see the visual representation of adding and subtracting complex numbers. In fact, it'll be much easier than you think it is. Trust me. Okay, so first of all, the visual representation is done on a complex plane. And this right here is a piece of the complex plane. If you see any similarities to the normal plane, the coordinate plane or the Cartesian plane, you're right. It's the same thing. It has two axes and it's a big giant grid of squares. But the axes are not x and y in this. Instead, a complex number, a plus bi, is made up of two parts, the real part and the imaginary part. So the axes will be the real and the imaginary part. So it's denoted by REZ and IMZ. In this case, RE stands for real and IM for imaginary, and the Z denotes a complex number. So these are the two axes. And let's just assume they're scaled by 1 here. Okay. So last time, if you remember, we added, let's take a random example, 2 plus 3i and 3 plus 4i. Isn't that right? And if you do it just by writing it down, it's pretty simple. You go ahead and add the imaginary and complex parts to get 5 plus 7i. But how do you graph these on the complex plane? Well, each complex number, a plus bi, corresponds to the point a comma b on the Cartesian plane. So this we can recognize because this is the x coordinate and this is the y coordinate on a normal plane. But instead, it's just written in a plus bi format. So if we were to graph a comma b, or let's say we take 2 plus 3i as the example. This corresponds to the point 2 comma 3. We know how to graph 2 comma 3. We just go 2 to the right and 3 up on the normal plane. Similarly, on the complex plane, we do the exact same thing. 2 right and 3 up will give us that point there. And all we do is draw a line. This denotes the complex number 2 plus 3i. Then similarly, 3 plus 4i, let me do this here, 2 plus 3i. 3 plus 4i would be corresponding to the point 3 comma 4 on the complex plane, which means you have to go 3 right and 4 up. And that gives us the point. This would be 3 right, 4 up, and that's that point, and we draw a second line. Now notice something common when you're drawing complex numbers. You always start from the origin. Complex numbers are not exactly a point on the complex plane. In fact, they're kind of like the line to that place. And you'll see why that's so. Now, if we added them, we'll get 5 plus 7i, which denotes the point 5 comma 7 on the complex plane. And we have 5 right here and 7 up there. So our point is there. So as you can see, there are some complex numbers, this one there. Now it's a little thin, but here's the general idea. Now, let me show you a trick. In fact, I'm just going to erase this line to show you something interesting. What if I take this 3 plus 4i and I move it up over there? Look at that. It matches so perfectly. You think that's a coincidence? I don't think so. Let's do another one. Okay. So let me switch colors. Right. So now let's say we have the complex number 1 plus 2i, and we want to add to that 5 plus 4i. What's this going to give us? Well, we add up the imaginary parts and the real parts to get 6 plus 6i. Let's graph them on the plane. 1 plus 2i would be right there because it corresponds to the point 1, 2. Then 5 plus 4i corresponds to the point 5, comma 4. And 6 plus 6i corresponds to the point 6, comma 6. So now we just have to graph 5, 4, and 6, 6. 5, 4 is there, and 6, 6 would be there. So the complex number 1 plus 2i is this complex number right here. The complex number 5 plus 4i is this one here. And what do we get when we add them? Well, according to our calculations, we should be getting 6 plus 6i, but let's see if that's true. If I take this number and I move it up here, look at that. It adds up directly to 6 plus 6i. Now, this should make sense, right? If you're familiar with vector addition, then you should see this very clearly. All you're doing is going 1 plus 2i, and then from that point, you're going 5 plus 4i. That's what it means, right? So let's use the same example, and if you describe it in detail, here's how it'll be. You start and you go from 0. You always start at 0, and then you go 1 plus 2i because that's the first number we're taking. So that means you go 1 here and 2 up. So we're essentially going here. 1 plus 2i, we're going up there. Then 5 plus 4i, we go 5 to the right and 4 up. So from here, the complex number 5 plus 4i is actually located there. But if you were to go 5 plus 4i from this point, it wouldn't be like that. You have to go 1, 2, 3, 4, 5 to the right and 4 up. So you'd have to get that number. And if you see, you'd have to go all the way there. So now if you look at it, this number, this point here, this complex number is actually 6 plus 6i. So complex numbers, you can think of it as adding them head to tail. So if we were to do that again, 1 plus 2i would be here. This is the head, and this is the tail, right? That's the tail. Then 5 plus 4i would be there. And that's the head of this complex number. Whoops, I made a mistake. It has to start from the origin. Okay. In this case, this is still the head, and this is still the tail. Right, so now, by adding head to tail, it means we connect the head of the first complex number with the tail of the second. So essentially what we're doing is taking this line, moving it so that its tail matches up with its head, and then whatever path you trace out there, whatever path you trace out, wherever you end up, that's your new complex. That's your sum. That's what you're looking for. And that complex number, again, you take it starting from the origin, and that sum is 6 plus 6i for this example. So if we were to just generalize this, then what all we'd say is if we had the complex number a plus bi corresponds to the point a comma b on the Cartesian plane, and if we had c plus di as our second number, corresponds to c comma d in the Cartesian plane. Now, if we were to start it, if you start 0, go to a comma b, then go to c comma d, we'd have to go c to the right of a and d to the top of b, not just d to the top of 0. So if we were to add these two, even on the Cartesian plane, you'd see it'll become a plus c comma b plus d, right? Now, what does this correspond to? This corresponds to the complex number a plus c plus b plus di. Is it right? And if you remember, we did get this result last time. If we just add these two, you'll get a plus c and b plus di. Simple. Similarly, we can do subtraction on a complex plane. Now, subtraction, if you're the most important thing to remember about addition is head to tail, right? Head to tail. Subtraction is just a tiny bit different. Instead of head to tail, it's head to head. And you'll see how that is. Now, let's take the same numbers 5 plus 4i, and I want to subtract 1 plus 2i. What will I get? Now let's try, well, let's just solve it without doing it, without actually graphing it. If I subtract, I'll have 4 in the real part, 2 in the imaginary part to get 4 plus 2i. Then let's graph these points. This corresponds to the point 5, 4. This corresponds to the point 1, 2. And finally, 4 plus 2i is the point 4, 2. So 5, 4 would be right there. 1, 2 would be over there. So these are the complex numbers 1 plus 2i and 5 plus 4i. Now I want to subtract 5 plus 4i minus 1 plus 2i. So the bigger minus the smaller, just for information. We should be getting 4 plus 2i, which actually happens to be this one right here. How's that? Well, watch this trick. Actually, wait. Let's see this. Has to be this one over here. Now watch this. If I take this line and I move it so that the head of that line connects with the head of the other complex number, you'll see that it goes exactly 4 up, and then it comes down by the second complex number, resulting in this point here, which is 4 plus 2i. Now, if you notice, we added the heads of the complex numbers. So complex numbers are subtracted by connecting their heads. Well, this might not seem particularly intuitive at first, but if you think about it, if you take the complex numbers z and w, z minus w, if we're trying to find z minus w, well, this complex number is the same as what you add to w to get z. So if I were to say w plus something equals z, then the something would be z minus w, correct? So the difference in the complex numbers z and w is what you add to w to get z. So now, if we were to go back to this complex number, 1 plus 2i and 5 plus 4i, here's how it'll be. Okay. Now you see, we have to add. So in this case, we're taking the first number here is z, and the second one is w. So this is z and this is w. So what do we have to add to w to get z? Now, using our knowledge of what we just discovered about complex number addition, if you add this complex number right here, you'll get to z. And if you noticed, this is the same complex number that we found as the result. Because if I drag it and make it start from the origin, look where it lands. 4 plus 2i. Isn't that right? Right. Okay, so let's go back to the original position, and it's over there. Now, you have to go 4 to the right, go 1, 2, 3, and 4 to the right, which means you have 4 as a real part, and 2 up, which means you have 2 as the imaginary part. And there's your answer, z minus w. It's as simple as that. So, in other words, if you have the complex number a plus bi and you want to subtract c plus di, this corresponds to the number a comma b, and this to c comma d. So the essential idea is from A you have to go C down, and from B you have to go D down. Now, the important thing to remember is if C or D are a negative number, you go up. Isn't that right? So if we had to do 3 plus 4i, for example, and we subtract 1 minus 2i, you do 4, and you have to go negative 2 down, or 4 or 2 up. Isn't that right? Yeah. So in this case, if we were to just do it out of coordinates, you still get a minus c comma b minus d. What does this make? A minus c plus b plus di, b minus di, on the complex plane. And sure enough, if you actually do it out here, you'll get a minus c plus b minus di. And in fact, this is exactly what we found in the last video. Now, there are many more things you can do with complex numbers. In fact, you'll find in geometry many times, especially in geometry relating to do with the coordinate plane, if you translate everything and put it into the complex plane, it's much easier to work with than with coordinates. It's because the addition system of complex numbers and the addition, subtraction, multiplication, and division, the system is so easy to do compared to coordinates. And there is a visual representation of multiplication and division, but we're not going to be doing that because that requires a decent amount of knowledge of polar coordinates, which you will find in, yeah, it needs kind of polar coordinates and the exponential form of complex numbers. And if you wanted to know, complex numbers, the exponential form is generally written in the form re to the power I theta. And this basically just stands for r cos theta plus ri sine theta. Ri sine theta. Yeah, it also goes into a little trig, so. Now, let's take the coordinate plane, or the complex plane, one more time. Now, if I give you the complex number, let's take this complex number, which happens to be 4 plus 5i. This complex number is 4 plus 5i. Now, 4 plus 5i tells you the location of the complex number in the plane. But if we wanted to find the magnitude of that complex number, or the distance from the origin of that complex number, which means from this point, if we travel all the way there, what is that distance? How can we tackle this problem? Well, let's see. 4 plus 5i, which means you go right 4 here. Is that right? So this length is 4. And you go up 5, which means this length has to be 5. Then, from here you can see it's a straightforward application of the Pythagorean theorem. It tells us this side, if it's side x, then x squared is equal to the square is equal. X is actually equal. Let's just write it as x. X is equal to the square root of 5 squared minus 4 squared, or 5 squared plus 4 squared, which is 25 plus 16, which is 25 plus 16, 41. X is the square root of 41. So now this length is actually root 41. So the complex number 4 plus 5i has magnitude of root 41. And here's how we denote this. The magnitude symbol is actually something you will have seen before for sure, and it's 2 bars. You may recognize this as the absolute value symbol also. An absolute value also does denote magnitude, but in complex numbers it's a little different. We found this to be the square root of 4 squared plus 5 squared, which is root 41. Isn't that right? So now if we take a number a plus bi in general, let's draw these graphs again. Now we have a new problem here. What is the magnitude of a plus bi? What is this answer? Well, we can construct a similar problem, but we'll choose a random point there and connect it. And A is this length here. So this is A. Whoops. A is this length here. And B is the length up. So if you want to find this length, if we call it C, then you know C is the square root of A squared plus B squared by the Pythagorean theorem. Therefore, this length here is the square root of A squared plus B squared. And this is pretty much the distance formula on the complex plane. So if you can see the similarities between the complex plane and the Cartesian plane, it's so similar that you wouldn't even realize it just yet. But there's one more thing we have left to do. Drawing the graph one more time. This time, it's going to be, we're going to have the first and fourth quadrants involved. Okay, so if you have the real axis and the imaginary axis, and I'm going to take, if you remember from the last video, we discussed one operation, which is conjugation. So the conjugate of A plus BI, denoted by a bar above it, is equal to A minus BI. So if we take 2 plus 3i as an example, the conjugates would be, the conjugate of 2 plus 3i would be 2 minus 3i. So let's graph these two complex numbers on the complex plane. 2 plus 3i would be there because that's 2, that's 3. And negative 3 would be down here. So 2 minus 3i is down here, literally. Now, if you notice, these are just reflections of each other over the real axis. Remember, I always made this mistake of saying the x-axis, but it's not the x-axis, it's the complex plane. Instead, it's the real axis. So conjugation reflects your complex number over the real axis. And it's clearly seen over here. Now, similarly, we could say the same for A plus BI, right? Because when we're switching from A plus BI to A minus BI, your A coordinate stays the same, which means if I was, let me draw a mini graph here. Your real parts is exactly the same and doesn't change. So if you were to go a random A in this direction and a B in the upward direction, you will end up with that random number. And negative b is exactly down the same length in the opposite direction. And as you can see, a plus bi and a minus bi are indeed reflections of each other over the real axis. That's the important thing to know about complex numbers. Now, let's do something interesting here. Let's multiply. I'm going to multiply a complex number by its conjugate. So I want to multiply a plus bi by its conjugate, which is actually denoted by a bar above this, right? But we know its conjugate is a minus bi, right? This is the conjugate. And we know from the difference of squares formula that this is in fact a squared minus bi squared. This is just a simple application of the difference of squares, which is a squared minus b into I squared is negative 1, or actually b squared here. So a squared plus b squared. Now this looks really familiar. We found that the magnitude of complex number a plus bi is equal to square root of that value we just found. So if we square both sides, then you'll get the magnitude of a plus bi squared is equal to a squared plus b squared. And this is equal to a plus bi times the conjugate of a plus bi. This is a really important identity to remember. In fact, what oftentimes you're never going to see a plus bi. Complex numbers are always denoted by z. Just like in math, when you're solving algebraic equations, you use x. Complex numbers are z. So if you take the z, then you have a complex number z multiplied by its conjugate. So z times the conjugate of z is equal to the magnitude of z squared. This identity is probably the most important identity in all of complex numbers to remember. This can come in so handy when solving problems and when you're simply trying to do anything on the complex plane. That's it for this video. Thank you so much for watching. Wish you a happy new year and hope 2021 is going to be awesome and much better than this COVID-filled year. Thank you for watching. Please subscribe to my channel and leave this video a like. See you next time.